Welcome back, everyone, to our deep dive into the world of math. We've been on this incredible journey exploring all sorts of cool math ideas, and today, we've got something really interesting lined up. It's permutations, but not just any permutations. We're talking about permutations without consecutive elements.
Oh, yeah, those are fun.
They are fun. But before we dive in too deep, let's just imagine for a second we're shuffling a deck of cards, right?
Yeah.
But here's the twist. We don't want just any random order. We're looking for those special arrangements where no two cards with, consecutive values are next to each other.
So no, like a king next to a queen or a 7 next to an 8.
Exactly. That's the whole idea. No consecutive numbers side by side. Now, to help us make sense of this all, we have a true expert in the house, a Fields Medal-winning mathematician who specializes in combinatorics.
Oh, that's a mouthful. But yeah, combinatorics is basically the art of counting and arranging things. Like figuring out how many ways you can order those cards with our special rule.
Right. And that's what I find so fascinating about this whole thing. Okay, we can picture what these permutations without consecutive elements look like.
Yeah.
But how do we actually count them? Especially when the set of numbers gets really big.
Yeah, that's where things get really interesting.
It does. Because, if you just try to list out every single possibility, it seems like it would take forever. Especially as the set grows larger. It'd be like trying to count all the grains of sand on a beach.
You're exactly right. It's not a simple task. And as you increase the number of elements, the number of possible permutations just explodes. It grows factorially. A brute force approach where you try to just list out every possibility is going to hit a wall pretty quickly.
Yeah, I was looking at the source material for this deep dive, and they even mentioned using Python code to do this brute force calculation. Is that just to show how difficult it gets, or is there ever a practical reason to do it that way?
It's mostly to illustrate the point. It works fine for small sets. But when you start dealing with larger numbers, it quickly becomes impossible. Like trying to use a bicycle to travel across a continent. Possible in theory, but not really the best way to do it.
Okay, so brute force is out. Then what tools do mathematicians use to tackle this kind of problem? There's got to be a more elegant way, right?
Well, there is, and that's where the beauty of math really shines through. Instead of trying to count each and every permutation individually, we can use a clever tool called a recurrence relation.
Recurrence relation. Okay, now that sounds kind of intimidating. Can you break that down for us? What exactly is a recurrence relation?
Sure. Basically, a recurrence relation is a way to define a term in a sequence based on the terms that come before it. It's like a pattern that connects each step to the steps before it. Think about the Fibonacci sequence, for example.
Yeah.
Where each number is the sum of the two numbers before it.
1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, and so on.
Yeah. Exactly. That's a simple recurrence relation. In our case, the recurrence relation for permutations without consecutive elements tells us that to find the number of these special permutations for a set of size, and we just need to know the counts for sets of size n-1 and n-2.
So it's like building a staircase. Each step depends on the two steps before it. That's pretty neat. But wouldn't we still have to calculate the first few steps manually to get started? Kind of like laying the foundation for our staircase.
That's right. You need a couple of initial values to kick things off. But once you've got those, you can use the recurrence relation to efficiently calculate the number of permutations for much larger sets without having to list them all out. It's like having a shortcut that lets you skip ahead in the counting process.
Ah, I see. We're finding a pattern that helps us avoid a ton of work. I'm starting to see the elegance here. But what about when we're dealing with truly massive numbers, sets that just keep growing and growing towards infinity? Is there a way to describe how this count behaves as the set size gets ridiculously large?
That is a great question, and that leads us to an even more powerful tool, generating functions.
Generating functions. All right, now you're really testing my non-Fields Medal math skills. Can we unpack that a bit? What exactly are generating functions?
Think of a generating function like a special code that somehow manages to capture the entire sequence of those permutation counts. It's like having a blueprint that describes the whole structure all at once.
Our source material mentions something called the OEIS database. Is that related to generating functions?
Oh, absolutely. The OEIS, or Online Encyclopedia of Integer Sequences, is like a giant dictionary for these mathematical codes. It has this huge collection of sequences and their corresponding generating functions. It's like this amazing resource for mathematicians. Our permutations without consecutive elements, they're in there too.
So for our problem then, there's a specific generating function that holds the key to understanding how this count behaves as the set size just keeps on growing towards infinity.
Precisely. And the amazing thing is that this generating function helps us pinpoint what's called the dominant term. the part of the code that really drives how fast the sequence grows.
Okay, so what does this dominant term tell us? What's the big reveal here?
This is where things get really mind-blowing. As the set size gets really, really large, the probability of getting a permutation without consecutive elements, it actually approaches a fixed value 1 divided by e.
Wait, hold on. E, as in the mathematical constant E. The one that shows up in calculus and compound interest. What on earth is that doing here?
That's the amazing thing about math. This seemingly simple problem about arranging numbers leads us to this fundamental constant that pops up in all sorts of seemingly unrelated areas of math. It's a reminder that the world of math is full of these beautiful and surprising connections.
I need a minute to process this. So
Yeah.
you're saying that even though we're talking about arranging numbers randomly, there's this underlying mathematical structure, this connection to E that's governing how they behave. That's pretty incredible.
Yeah, it really is. And it highlights the power of generating functions. They allow us to zoom out from those step-by-step calculations of recurrence relations and see the bigger picture, the asymptotic behavior of these sequences. It's like having a bird's eye view of the whole landscape.
So I've gone from trying to count every single possibility to using recurrence relations and now these super powerful generating functions. It's amazing how these different math tools come together to help us solve this one problem.
It speaks volumes about the beauty and interconnectedness of math. We started with this basic question about arranging numbers and ended up with this profound insight about how these special permutations behave as the set size grows and their connection to E.
And to think it all comes down to this one special number E. It's like a hidden code that unlocks the secrets of these permutations. But what does this one divided by E probability actually mean? Does it have any real-world significance?
Now, that's a fantastic question, and one that gets to the heart of why this seemingly abstract math problem is so intriguing. The fact that the probability approaches a fixed value as the set size grows means there's a limit to how often these special permutations happen. This hints at some kind of hidden order within all that randomness. It's like finding a pattern in what looks like pure chaos.
So even though we're dealing with randomness, there's this underlying predictability. That's a powerful concept.
Yeah.
Makes you wonder if there are other seemingly random events out there that might exhibit similar patterns.
You're spot on. This idea of finding order in chaos, it's a recurring theme in mathematics, and actually way beyond math, too. It often leads to some pretty surprising insights. It really is. And, it highlights just how powerful generating functions can be. They give us this way to zoom out from those step-by-step calculations we were doing with the recurrence relations and see the bigger picture, the asymptotic behavior of the whole sequence. It's like we're getting a bird's eye view of the whole landscape.
Okay, so we've gone from brute force counting to recurrence relations, and now we've got these super powerful generating functions. It's pretty amazing to see how these different mathematical tools all work together to help us crack this problem.
It really is a testament to the beauty and, the interconnectedness of mathematics. We started with this simple question about arranging numbers, and it's led us to this profound insight about how these special permutations behave as the set size grows and their connection to that special number E.
And to think that it all boils down to E. It's like this hidden code that unlocks the secrets of these permutations.
Yeah.
But what does this one divided by E probability actually mean? Does it have any real-world significance?
That is a fantastic question. And it really gets to the heart of why this seemingly abstract math problem is so fascinating. The fact that the probability approaches a fixed value as the set size grows, well, it means there's a kind of limit to how often these special permutations can actually occur. It hints at some hidden order within all that randomness. It's like we're finding a pattern in what seems like pure chaos.
So even though we're dealing with randomness at its core, there's this underlying predictability. That's a pretty powerful concept. It makes me wonder, are there other seemingly random events out there that might actually exhibit similar patterns?
You are right on the mark. This idea of finding order within chaos. It's a recurring theme in mathematics, and actually way beyond math, too. And it often leads to some pretty surprising and insightful discoveries.
This whole deep dive has been a real eye-opener. It's just fascinating to see how we start with a simple question about arranging numbers and end up uncovering these really deep mathematical connections.
It really is a testament to the beauty of math, isn't it? There's always more to discover if you just look beneath the surface.
So for our listeners who might be feeling inspired to explore further, what are some related concepts they might find interesting? What could they dive into next?
Well, one really fascinating area is something called derangements. These are permutations where none of the elements end up in their original position. So if we were arranging the letters A, B, C, D, E, a derangement would be an arrangement where A is not in the first position, B is not in the second, and so on.
Oh, so it's like musical chairs. Everyone has to switch seats.
Exactly. And you know what? Derangements, they have their own surprising connections and patterns, just like our permutations without consecutive elements. Lots to explore there.
I think we've given our listeners plenty to ponder today.
Uh,
A huge thank you to our Fields medal-winning guest for guiding us through this incredible mathematical landscape. It's been a privilege.
The pleasure was all mine. I always enjoy sharing the wonders of math with a curious audience.
And to our listeners, thank you so much for joining us on this deep dive into the world of permutations. We hope you've come away with a new appreciation for the elegance and the interconnectedness of mathematics. Until next time, keep those mathematical minds buzzing.
It really is a testament to just how much beauty there is in math. There's always something new to discover. You just got to look a little deeper.
Absolutely. And if any of our listeners are feeling like they want to explore a bit further, what are some related ideas or concepts that they might find interesting? What should they dive into next?
Well, one area that I find really fascinating is something called derangements.
Derangements.
Yeah, derangements are permutations where no element ends up back in its original spot. So if we were arranging the letters A, B, C, D, and E, a derangement would be an arrangement where A is not in the first position, B is not in the second position, and so on.
Oh, so it's like a game of musical chairs where everyone has to switch seats.
Exactly. And it turns out derangements have their own set of really interesting connections and patterns, just like the permutations without consecutive elements that we've been talking about.
Well, I think we've given our listeners plenty to think about today. A big thank you to our guests for walking us through this incredible mathematical landscape. It's been a real privilege having you here.
The pleasure was all mine. I always enjoy sharing the wonders of math with a curious audience.
And to all of you listening out there, thank you so much for joining us on this deep dive into the world of permutations. We hope you've come away with a new appreciation for the elegance and the surprising interconnectedness of mathematics. Until next time, keep those mathematical minds buzzing.